Our home planet, planet Earth, acts like a great recycling machine. All the atoms on Earth are used over and over again. The sun's photons and the Earth's deep interior heat provide the energy to drive the movement of these atoms from one reservoir to another. There are numerous geochemical cycles, but the big three are the cycles of water and rock and air. And in Lecture 41, I'll focus on the atmospheric cycles of weather and climate, which are driven by the sun's radiant energy. The outline of this lecture is straightforward. After reviewing the nature of cycles in general and the water cycle in particular, we're going to look at the atmospheric cycle. We commonly talk about the atmosphere in terms of its short-term variations, that's the weather, and also its long-term variations, that's climate. Now, to do this, I have to tell you about 5 familiar atmospheric variables. These variables are the temperature, the air pressure, the humidity, and then the closely related variable of cloudiness and the prevailing winds. And then in the last third of the lecture, I'm going to shift focus to consider some of the factors that influence global climate and its variations. So in this lecture, as in the last, I'm exploring Earth's great cycles of water, air, and rock. Recall that all cycles involve 2 distinct kinds of information. First, you need to make an accounting of all the different reservoirs. So water is found in 6 major reservoirs. That was the oceans and the ice caps. There's lakes and rivers, groundwater, the atmosphere, and finally life itself. And then it's necessary to define the ways that material move among the different reservoirs. So water moves through the atmosphere by evaporation and precipitation. It flows in rivers by gravity, and it flows in the ocean by currents, and from ice by sublimation and by melting. Now, in talking about geochemical cycles, I focused on 4 characteristics that are shared by all geochemical cycles. Now, the first one, all cycles involve movements of matter between reservoirs. So that's what cycling is. So, of course, water moves between its various reservoirs. It evaporates from oceans. It rains on the land, and so forth. And then all cycles also require some source of energy. And in the case of water, most of the cycle is driven by energy from the sun. Of course, if lots of water gets subducted and reworked into the Earth's mantle, then the Earth's heat's also going to play a big role. Another aspect of these cycles is that they can be altered by human activities. So humans mine water in underground reservoirs, and they can seriously deplete these reservoirs, as we saw in the case of that High Plains aquifer. And finally, all these cycles are interrelated. The water cycle influences the rock cycle by erosion, and as we'll see, water plays a central role in weather and climate. Well, I'd like to step back for a moment and think about these cycles in the context of some of the great principles of science. After all, every physical system, including cycles of Earth materials, have to obey natural laws. And this is a good way to underscore how interrelated all these scientific principles really are. So for one thing, atoms are conserved. So we saw that the total amount of water on Earth is more or less constant. The same molecules, they cycle over and over again. Matter just doesn't appear or disappear. And then there are Newton's laws of motion, which say that if matter moves, a force has to be involved. The force of gravity causes liquid water to run downhill in rivers and streams, and it causes water vapor to mingle with the rest of the atmosphere. And then there are the laws of thermodynamics. They said that a source of energy is required to exert a force over a distance. So heat energy from the sun provides the energy to evaporate water. And then the Earth's heat drives the movement of water in geysers and volcanic vents. We also saw that energy can change from one form to another. So the sun's radiation is used to evaporate water, and that's converted to gravitational potential energy, and then we use some of that energy in hydroelectric power plants to light our lights. And heat has to spread out in accord to the second law of thermodynamics. Water plays a big role in that movement of heat. For example, surface ocean currents transfer heat across the globe from equator towards the poles, while cooler water circulates from poles towards the equator in deep ocean currents. And so in the rest of this lecture, and the next as well, we'll see how these same principles apply to the great cycles of the atmosphere and of rocks. Now, the Earth's atmosphere, it's an envelope of gases that surrounds our planet. 99% of that envelope is within about 32 kilometers of the surface, but a tenuous atmosphere extends up to hundreds of kilometers higher up. Now, at first glance, It might seem odd to speak of an atmospheric cycle. After all, the atmosphere appears to be one continuous mass of air rather than several distinct and different reservoirs. But it turns out that at any one time, the atmosphere can be divided into separate air masses, and each of these air masses has more or less uniform properties. So each air mass can be thought of sort of as a separate reservoir of air, and any two adjacent air masses are going to differ to some extent in their physical properties. Now, adjacent air masses often occupy different regions close to the ground. In this weather map, you see there's several different air masses. They're designated H and L for high and low pressure systems. Now, I'll tell you more about pressure in a few minutes, but suffice it to say that these air masses move as large pieces of the atmosphere. So on any given day, you might have a big low pressure system in the Midwest and an adjacent high pressure system in New England's coast, for example. It's also possible for adjacent air masses to represent distinct atmospheric layers. These are layers high above the surface. So the layer called the troposphere, which extends up to about 10 or 15 kilometers, is generally a separate air mass from the stratosphere, which extends from about 15 up to about 50 kilometers. Now there's some mixing, but for the most part, they're distinct bodies of gas. Before I get to the discussion of the properties of air masses, I have to define two familiar terms that are quite closely related. That is the weather and the climate. Okay, weather is simply the state of the atmosphere at a given time in a given place. So weather is really a local phenomenon. It's highly variable. You know how weather can change dramatically from one hour to the next. For example, if a storm front comes through. At any given place, the weather is going to be influenced by many factors, so it's highly variable. Even the variability of weather is highly variable. In places like Santa Barbara, California, or the desert Southwest, or the west coast of Maui in Hawaii, the weather's pretty much the same almost every single day. By contrast, on the east coast of the United States, or near the Great Lakes, or in the high Rocky Mountains, weather can change amazingly fast. Now, climate, on the other hand, it's a long-term average of weather for a given region. So regional climate may be hot or cold, it can be wet or dry, though the weather on any given day might be quite different from that average. There are some temperate regions where the climate includes 4 seasons that may themselves contrast very sharply, like summer versus winter in New England and the Midwest. A region's climate may remain unchanged for centuries, but studies of ancient climates reveal that an area's climate may also shift quite dramatically in a matter of just a few years, often for reasons that are as yet uncertain. Now we come to the 5 variables that define the state of the atmosphere. These variables are the temperature, the air pressure, humidity, cloudiness, and prevailing winds. Your local weather report typically covers all of these variables in one way or another. So let's look at each of them. The temperature of the atmosphere is actually a rather complicated variable. See, the temperature reported in daily weather predictions refers to temperature at ground level in the shade at a particular time. But temperature in any one locality can vary quite widely depending on the time of day and the amount of sunlight and the elevation above the ground. For the record, the highest average daily temperature on Earth is 94 degrees Fahrenheit. That's at the Danakil Depression in Ethiopia. And the coldest place on average is 70 degrees below 0 Fahrenheit. That's at Plateau Station in Antarctica. Now, temperature varies strongly with altitude above the ground. In fact, the temperature variations are used to define the major layers of the atmosphere. Atmospheric scientists recognize quite a few distinct layers. I'm only going to consider the first 2 layers, that's the troposphere and the stratosphere. Take a look at this diagram. First, we have the troposphere. That extends from the ground up to anywhere from about 10 to 16 kilometers. That layer is defined as a zone in which temperature decreases with altitude. So this is the air mass that experiences extensive convection from the ground. As air near the ground is heated, it rises through the troposphere and it's cooled. So the troposphere layer is actually thicker near the equator than it is at the poles. Then the next layer up, that's here, it's called the stratosphere. It extends from about 15 kilometers up to about 50 kilometers. Now temperatures in this zone actually increase with elevation, often by as much as 50 or 60 degrees centigrade. That's because small quantities of the gas ozone in this layer absorb much of the sun's ultraviolet radiation. And naturally, if the atmosphere absorbs energy, it's going to get warmer. Now the second variable that we use to define the state of the atmosphere is pressure. Pressure is defined as a force acting on an area. Remember that the atmosphere is made of gases. Those are atoms and molecules with mass. Now gravity is pulling down on the column of air above you, so the pressure at sea level, that's about 14.7 pounds per square inch. That's actually the weight of the air. So air pressure decreases significantly with altitude because air is compressed by its own weight. So at a height of 5.5 kilometers, that's a bit higher than the elevation of the tallest Rocky Mountains, air pressure is only half of the value at sea level. Now most jet airliners fly at perhaps 12 kilometers, where the pressure is only about a quarter of the surface value. That's why cabins have to be pressurized. And at a height of 32 kilometers, which is far above the flight paths of jetliners, air pressure is only about 1/100th of that of sea level. Now, atmospheric pressure also varies laterally, though not by nearly so much as vertically. This lateral variation occurs because air masses tend to move and rotate with respect to each other. Look at this. As a result, air can pile up in some places to form a high-pressure system, while it stretches out in other places to form a low-pressure system. Even so, the atmospheric pressure at sea level doesn't vary by more than a few percent from its average value of 14.7 pounds per square inch. By the way, weather reports often use the odd pressure units of inches of mercury. Well, that's a throwback to early science apparatus that used a column of mercury liquid in a sealed glass tube. The weight of all the atmosphere pushing down on mercury is equivalent to the weight of a column of mercury about 30 inches high. Now, even though the pressure differences are rather small, these high and low pressure systems have a big influence on weather. The air in the low pressure systems tends to rise. That causes cooling and increased clouds. And conversely, high pressure systems tend to feature warmer, drier air. And here's another pressure-related effect. A significant air pressure difference can occur at the boundary between the thicker equatorial troposphere and the thinner polar troposphere. This pressure difference causes high-speed air currents called the jet stream. Now, the jet stream moves west to east across the United States, and this is a significant effect. For example, you may have noticed that the jet stream causes flights from New York to Los Angeles to average almost an hour longer than flights from LA to New York. And the jet stream also varies quite a lot. Look at this. It can move farther north or south or develop these rather large bends. And those variations can cause big changes in our weather patterns. The third atmospheric variable is humidity. That's a measure of the atmosphere's highly variable water content. Now, look at this. To understand the significance of humidity, it helps to see the bulk composition of the atmosphere. For the most part, that composition is remarkably uniform. Look at this. Two gases, nitrogen here and oxygen, they make up 99% of dry atmosphere. Now, nitrogen in the form of N2 molecules or dinitrogen gas is the most abundant. That's about 78% of the atmosphere's volume. Now, recall that nitrogen is element 7 and wants 3 more electrons to reach a magic number of 10. So it forms a covalent triple bond with another nitrogen atom. That gives nitrogen, N2, the molecule. And nitrogen is a relatively inert and non-reactive gas. The covalent bond, you see, is very, very strong. It's not easily disrupted. So the atmosphere's nitrogen is stable, and the atmospheric nitrogen budget is relatively fixed. And then there's oxygen. Oxygen, primarily in the form of O2 molecules, accounts for 21% of the atmosphere's volume. Now, O2 also forms a pretty strong covalent bond. Oxygen is element 8, and so it wants 2 more electrons, so it forms a covalent double bond with another oxygen atom. Now, even so, oxygen is relatively reactive, and it readily takes part in those oxidation reactions. That means oxygen readily accepts electrons, for example, from carbon to form carbon dioxide. That's the fizzy bubbles in soda water. Or oxygen can take electrons from hydrogen to form dihydrogen oxide. That's water. Or remember, from iron to form iron oxide, which is rust. Now, atmospheric oxygen is a byproduct of plants during their process of photosynthesis. In fact, the presence of lots of oxygen in our atmosphere is so closely tied to life that a lot of scientists argue that discovery of another planet with an oxygen-rich atmosphere would be a sure sign of extraterrestrial life. Now, the atmosphere also contains minor amounts of other gases. There's about 1% by volume in the atmosphere of the inert gas argon. That's element 18. You know, argon was sufficiently abundant that it was the first of the inert gases to be discovered. Then the entire last column of the periodic table, including helium and neon and so forth, quickly followed that discovery. After argon, the other gases in the atmosphere are pretty minor. there's about 35 thousandths of a percent carbon dioxide and smaller traces of a dozen other gases. Actually, some of these trace gases, such as ozone, can reach unhealthy levels in regions of high air pollution. So, with that background on atmosphere composition, when it's completely dry, we can look at humidity. The humidity is a measure of water vapor as a constituent of the atmosphere. The atmosphere always contains some water vapor, though the amount is highly variable. The amount of water vapor depends on the temperature. It also depends on the relative humidity. Now, relative humidity is given as a percent on a scale where 100% relative humidity means the air is completely saturated with water. Usually when the relative humidity hits 100%, it's raining or it's snowing. Now, in this regard, temperature is a major effect because warm air can hold a lot more water than cold air. Look at this graphic. You'll see what I mean. The water vapor pressure can vary by more than a factor of 1,000 at the Earth's surface. Air on a cold, dry winter day might hold less than 0.1% water by volume. That's pretty dry. Think about how dry your lips get on a cold, dry winter day. By contrast, air on a hot, humid summer day may contain almost 10% volume water. That's amazing. And if you've ever been in a tropical climate, you know how heavy the air can feel and how monsoon rains can dump buckets of water. All right, cloudiness is the fourth atmospheric variable, and it's closely tied to humidity. Clouds represent a concentration of tiny water droplets or ice crystals. Ice crystals effectively scatter light, so clouds appear to be white. Clouds form when air becomes saturated with water. That's a process that occurs often when a mass of air rises and cools. Clouds often dramatically outline the contact between two adjacent air masses, especially when one air mass is cooler and drier than the other one. You often see layers of clouds at the boundary between the troposphere and the stratosphere, for example. So a band of clouds will also very often mark a cold front where two air masses at different temperatures collide near the ground. Look at this. One of the commonest examples of this phenomenon is the line of dramatic anvil-shaped thunderhead clouds that often forms when a warmer air mass collides with a cooler air mass. Look at this diagram. See what happens. The warmer air mass, it's less dense. So when the two air masses meet, the warmer air rides up over the cooler air, and this increase in elevation acts to cool the warm, wet air, and that in turn leads to clouds and to rain. And there are other effects as well. There are large gradients in temperature and in pressure, and they generate strong winds and violent lightning. Now, a very similar effect sometimes occurs in mountainous areas. See, clouds and rain often form on the windward side of the mountain. That's as warm, wet air mass is forced to rise up the mountain flanks. And then the leeward side of the mountain is usually much drier. My favorite example is the Hawaiian Islands in the middle of the Pacific Ocean. See, warm air moves east to west, thousands of kilometers across the Pacific. It picks up moisture. Then the air mass runs smack into the 10,000 plus foot high mountains of Hawaii. And so as the air moves up and over the summits, it cools, becomes saturated with water. As a result, some of the mountainous areas of Hawaii receive an extraordinary 500 inches of rain per year on the eastern sides of the island. And that process effectively dries out that air. The air spills down the other side. So a few tens of kilometers away along the western shorelines, tourists enjoy day after day of sunny and dry beach conditions. The fifth atmospheric variable, that's wind, specifically the direction and the strength of winds. So wind can be described with a vector. That's an arrow for which the direction of the arrow is the same as the direction of the wind, and the length of the arrow corresponds to the wind's speed. Winds are the result of atmospheric convection. Now remember, convection, that's one of the most efficient ways to move heat, and that's exactly what wind does. It's a process that helps to redistribute heat on Earth's surface. Let me give you an example that will be familiar if you've ever spent time on the shore near a large body of water. Ocean breezes on a tranquil summer day, they illustrate how winds can occur. Now, during a sunny day, the land heats up faster than the water. So warmer air rises from the land. And as a consequence, cooler air flows in from the water, and that's a refreshing sea breeze. So that's the breeze you feel during the day at the beach. And then in the evening, as the land cools, the pattern reverses. Warmer air over the water rises, and the breeze comes from the land. Now, on a much, much larger scale, the prevailing winds arise in essentially the same way. Look at this diagram. See, sun heats air most near the equator. That air rises and it circulates toward the nearest pole. while colder air near the pole sinks and flows back towards the equator. Now, if the Earth didn't rotate at all, prevailing winds near the Earth's surface would follow the lines of longitude from poles to equator as on this figure. So in North America, all our winds would be from the north, and then winds at higher elevations would flow from equator to pole. But think about this. The Earth's rotation complicates this pattern by sweeping out that north-south convection. Look here. This motion divides the atmosphere into bands, east to west and west to east prevailing winds. Now, here's an actual map of some of these famous currents. Ships sailed from Europe to the Caribbean on the northeast trade winds. They're here. And then the ships returned on a more northerly route using the prevailing westerlies. They're shown up here. And recall how a similar situation can be seen in the banded atmosphere of Jupiter, which has an extreme version of this kind of global weather pattern. Okay, so far I've been talking about the weather. That's the short-term variation of the state of the atmosphere. But what about the longer-term changes in the average state? That's the climate. Now, climates seldom change much on the scale of human lifetimes. But new evidence suggests that the Earth may occasionally experience short periods of very dramatic climate change. By some estimates, we're now in the middle of a period of very rapid global warming. Climate change research is thus becoming a really hot research topic these days, and you'll see that lots of news stories that relate not just to the science, but also to the politics and the economics of predicted climate change. Year-to-year measurements of global temperature in recent years seem to indicate that the Earth is getting warmer at an alarming rate, perhaps a rate as high as several degrees per century. The average global temperature is admittedly extremely difficult to measure, but by all accounts, the 15 hottest years on record have all occurred since 1980. And what's even more disturbing, each of the past few years has been amongst the hottest ever recorded since record-keeping began in the 1870s. Now, as I said, this average global temperature is a really difficult number to measure. For one thing, most long-term sites of weather stations have become more urbanized. They occur at airports and in cities, which just keep adding more asphalt and more buildings, so these sites may tend to become what are known as heat islands. And some conservative politicians claim that global warming isn't happening at all, it's just that cities are becoming bigger and therefore hotter. A much, much better way to measure average global temperatures is to document ocean temperatures. Now, the water stores and distributes a huge amount of Earth's surface heat. The problem is that scientists haven't been measuring ocean temperatures in any systematic way for very, very many years. So it's difficult to see systematic trends. Now we have an array of global surveying satellites, so at least we're establishing a clear baseline for these future surveys. The complexities of this research are epitomized by widely reported satellite data from the late 1990s. I want to tell you about this. A satellite designed to measure global temperatures seemed to be revealing an overall cooling in the lower atmosphere, not a warming. And these results were reported and debated, and they may even have played a role in policy making. Only then it was realized that the measurements were flawed because the satellite's orbit was decaying, and that skewed the results. So after reanalysis, the same satellite data seemed to indicate a gradual warming trend consistent with other measurements. By the most optimistic estimates, the global average temperature is going to rise at least 2 degrees centigrade by the year 2100. But there are other scientists who estimate at least 3 times that increase. Well, so what? Why should we care if summertime's high temperatures are 5 or 10 degrees Fahrenheit hotter than they are now? Even if we have to pay more for air conditioning, the winter heating bill should be a lot less. But think in a more global sense. For one thing, such a climate change would cause a significant increase in sea level, perhaps by several feet by the year 2100. Well, hundreds of millions of people live in coastal areas. Some entire countries, including Holland and Bangladesh, a number of island nations, would be hard-pressed to hold back the oceans. And remember, most of the big cities in America, they're coastal cities, and they aren't that much above sea level. The economic consequences could be immense. Global changes in climate could also cause a major shift in agricultural lands. Those heavily irrigated lands in the south-central U.S. could become a dust belt, while the climate in central Canadian provinces could become much more productive for agriculture. Well, whatever the cause of the apparent warming trend and whatever its social and economic consequences, we've got to learn more about factors that affect climate. An important new scientific discipline, therefore, is paleoclimatology. That's the study of ancient climates, and they're revealed by a variety of evidence. So you have the distribution of fossil plants and animals. They provide important clues. See, fossil pollen grains revealed the distribution of plants with distinctive habitats. And then the fossil coral reefs indicate in areas of warm water. Rock types can also provide clues. For example, glacial features like gravel deposits and terminal moraines, they're especially distinctive. Now, ice cores from Greenland and Antarctica hold a continuous 250,000-year record of the atmosphere in the form of tiny air bubbles. And it turns out that the ratio of lighter oxygen 16 isotopes to the heavier oxygen 18 isotopes in the air is also a sensitive indicator of temperature. See, the warmer it is, the easier it is for heavy oxygen to enter the atmosphere from the ocean. Now, the ice core climate record seems to indicate that dramatic temperature changes can take place in very short periods. Both Greenland and Antarctica experienced temperature increases of 10 to 20 degrees centigrade in just a few decades. That was at the end of the glacial advance about 12,500 years ago. Some scientists suggest that that event was caused by a rapid rise in greenhouse gases. You could have carbon dioxide from volcanoes, which might be the culprit, or it could be methane from a sudden release of methane, which occasionally gets trapped on the ocean floor. Now, this is an especially disturbing possibility. It turns out that vast amounts of methane are trapped in ice on the continental slopes. If the ocean temperature warms too much, that could cause some of this methane ice to melt. And that methane would escape in the atmosphere, and that would accelerate the greenhouse warming, and this cycle could feed back on itself and cause catastrophic warming in a short period. We just don't know enough yet to say for sure. By the way, I'll examine the greenhouse hypothesis at greater length in Lecture 59. Now, one of the most intriguing aspects of climate studies is the growing realization of a strong link between climate and plate tectonic processes. The climate of a region is profoundly affected by details of the distribution of landforms and bodies of water. And of course, the distribution of landforms changes as the Earth's tectonic plates move. In spite of the many uncertainties about climate change, several factors that strongly influence regional climate are now well documented. These factors include ocean currents and large bodies of water, mountain ranges, and the position of continents themselves. Let's look at these factors. Now, large bodies of water and ocean currents can greatly change a region's climate by transferring heat. Recall that water has an extremely high heat capacity. It can store a relatively high amount of heat energy, and that means that large bodies of water moderate Earth's surface temperature, and currents can transfer heat quite efficiently. So, for example, look at this, the Gulf Stream. The Gulf Stream is a surface current that flows from near the equator to the eastern North Atlantic. The Gulf Stream keeps Great Britain relatively mild, even though it's farther north than Newfoundland. And then the California Current, which carries cool water from the Bering Sea along the California coast, that moderates the climate of San Francisco and Los Angeles. Oceans and large lakes can also affect climate by adding moisture to an air mass. Now, northwest New York State, it receives heavy rains and snows as air masses from Canada pass over the Great Lakes and pick up moisture. In a similar vein, hurricanes obtain their water from equatorial regions of the Atlantic Ocean in late summer and fall. That's when the ocean temperature is warmer than the air temperature. Then the ocean's warmth provides an energy source that strengthens the hurricane as it moves over water. And mountain ranges, they disrupt the movement of air masses. They can efficiently remove moisture from an air mass. I told you how high volcanic mountains in Hawaii affect rainfall. Well, locations just a few kilometers apart on opposite sides of a volcanic mountain can have radically different rainfalls. You know, I have to tell you an amazing story that was related to me by a Chinese geologist. There's an extensive mountain range that runs east-west across central China. That's over here. Now, those mountains block moisture from the southeast prevailing winds from reaching the vast northern deserts of Xinjiang province to the west and Inner Mongolia to the east. Those desert areas are dry, they're unproductive. The central region, by contrast, experiences devastating flooding, while the north is almost uninhabitable. So it turns out that some Chinese engineers have actually proposed leveling a portion of the central mountain range to redistribute moisture and provide new wet cropland. Now, even with the most advanced earth-moving techniques, such a project would take hundreds of thousands of workers, many, many decades to accomplish it. I think only the Chinese could think on such a grand long-term scale. These and other effects show that the movement of tectonic plates plays a major long-term role in Earth's climates. It's pretty obvious why this is so. As plates move, bodies of water open and close. Mountain ranges are formed. In addition, ice ages are strongly influenced by the presence of continents near one or both poles. Today, the continent of Antarctica is smack over the South Pole, while there's lots of land area above the Arctic Circle. So ice can build up in that lower sea level and increases the reflectivity of the Earth's surface to sunlight. But thanks to plate tectonic movements during other geological eras, there were no polar ice masses. Well, to summarize, I focused on two aspects of the Earth's atmospheric cycle. Those are the short-term variations of weather and the long-term variations of climate. Now, the state of the atmosphere is defined by 5 distinct variables. There's temperature, there's air pressure, humidity, then cloudiness, and finally the prevailing winds. The climate, on the other hand, may vary over long periods as a result of changes in atmospheric composition and because of the position of ocean currents and landforms such as mountains. Ultimately, then, the global cycles of water and air are tied to the great rock cycle of the solid Earth, and that's the subject of the next lecture.